Okie dokie. So, okay, let me introduce Professor Sean Carroll. So, Sean did his undergraduate in Villanova University, and then his PhD in Harvard under George Field. He did postdocs in MIT and UC Santa Barbara, and held faculty positions in the University of Chicago and Caltech. And he's now the Homewood Professor of Natural Philosophy at Johns Hopkins and fractal faculty at Santa Fe Institute. I don't know what that means, but it sounds. Okay, Sean is, of course, very well known for research on theoretical cosmology, gravitation, foundations of quantum mechanics, many other things. He has many prizes and fellowships that I'm not going to list, but he's also very well known as a prolific popularizer and democratizer of science through his writing and his public speaking and podcasting. So it's a pleasure to have him here telling us about philosophical issues in quantum thermodynamics. Please take it away.
Thank you very much. This is a title that I did not invent. I was handed this title and told to talk on it. Nicole told me to talk on it. So philosophical issues in quantum thermodynamics. I'm going to make two slight changes between the title and my content. I'm not going to talk about philosophical issues, and I'm not going to talk about quantum thermodynamics. But they're only very, very slight changes, and I will explain to you exactly what the changes are. So I think it sticks with the spirit of what's going on. So the reason why I'm not going to talk about philosophical issues is because I'm going to switch it to what I would call foundational issues. And if you want to sort of map the intellectual terrain here, there's philosophy, there's physics. Those are separate, but they are rubbing right up against each other. And there's philosophy of physics. And philosophy of physics, or philosophy of science even more broadly, is a big area. And you might talk about things like, what is a theory? What is scientific? How do you test theories? Stuff like that. All that is philosophy of physics. But then there's an area called foundations of physics that is truly overlapping between philosophy and physics. And the difference is that in philosophy of physics, you might study physics, like you're talking about how physics works. Whereas in foundations of physics, you're talking about nature. You want to figure out how the universe works. But you're doing it with a style that is maybe a little bit different than the typical physics department. So I made up these numbers, but roughly there's a breakdown where people in foundations of physics are either physicists with a physics PhD, physics PhDs who are now professors of philosophy, or people with philosophy PhDs who are now professors of philosophy. There's no people with philosophy PhDs who are professors of physics. Do not let that happen. Irreversible process to get a philosophy PhD. But the point is that, this is a caricature, but there's some truth in here. Physicists are laser focused on getting the right answer, figuring out what happens in the world. And you're nodding, you're like, that sounds like a good thing, getting the right answer. But the thing is, they're so focused on getting the right answer, they're entirely happy with getting the right answer for the wrong reason. Whereas philosophers are really, really focused on using valid arguments, getting the right reason, even if they reach the wrong conclusion. And in certain areas, you need to care about both. When you get to foundational questions, like what is the heart of, all the questions that you might dismiss because they're like definitional or things like that. What is reality and things like that? Like, you really need to make sure that you get the right answer for the right reason. Physicists are very happy to sort of say entropy increases, but there's lots of bad arguments for why entropy increases, and you can find them all in textbooks. So in the foundations subfield, you want to do a little bit of both. So for example, a physics question might be, what is the probability that you go from situation A to situation B? A philosophy question might be, what is probability? And a foundational question might be, is the universe fundamentally probabilistic? Or is that just something that, is a convenient approximation for us? So you might be thinking to yourself, well, I think about that. I care about that. Good. Then you care about the foundations of physics in specific, and, we welcome you to the fold. The other thing about quantum thermodynamics is that, interestingly, there has not been a lot of foundational work on quantum thermodynamics. There's been an enormous amount of foundational work on thermodynamics and statistical mechanics, and separately on quantum mechanics. And so the choice I was given in the talk was I could either invent some things that you could think about in the foundations of quantum thermodynamics, or I could just tell you some interesting things that I know in the foundations of thermodynamics separately and quantum mechanics separately, and figure that you are the experts in quantum thermodynamics. So my goal here is to inspire you to synthesize some of these questions and put to work what we know about quantum thermodynamics to address some of these foundational questions. I mean, there's foundational questions in everything, classical mechanics, quantum field theory, et cetera, but you really picked the two that are most popular for people in foundations to think about: quantum mechanics and statistical mechanics. These are things where we use them and we get the right results, we can do calculations. Why it works and what exactly is going on are things that there's very little consensus about in important ways. So that's what I want to sort of take you through. I will also, I'm kind of shameless, so I will drop in my own research results here and there, because I think those are the most interesting results in the field. There you go. So, and some of these questions are obvious and the answers are obvious. So here is a question you will certainly have come across already in your life. What do you mean by entropy? What's the right definition of entropy, right? And if this is a trivial question because the answer is obvious, there's no right definition of entropy. It depends on the question you're trying to answer. But nevertheless, we kind of forget that sometimes, and we get into arguments about what the right definition is. And there are different classes of definitions. So in the literature on the foundations of stat mech, we distinguish between sort of a Boltzmannian approach to entropy and a Gibbs-Shannon approach to entropy. The labels, by the way, with people's names are entirely ahistorical, because Boltzmann thought about the Gibbs-Shannon one and Gibbs and Shannon thought about the Boltzmann one. So don't worry about that. They're just labels. But the idea is between, if you like, a objective versus subjective version of entropy. So in the Boltzmann way of doing things, you have a space of states, microscopic states for some complicated system, and you coarse grain it. You invent equivalence classes that you call macro states. Maybe, so already there's a question in the foundations of physics. Who invents those macro states? How do you say that two microscopic states are macroscopically equivalent to each other? And there's purported answers. Well, maybe you have some observational parameters that you're going to say if they give you the same answers for temperature or density, et cetera. But clearly there's work to be done there. And then if you look at Boltzmann's tombstone in Vienna, there's an equation on it. I always tell my students at the most vulnerable part of their PhD careers, what is the equation that will be on your tombstone someday? Boltzmann never wrote down the equation that is on his tombstone. Planck wrote it down and then engraved it later, but the equation is S equals K log W. The idea is that W is the number of microstates in a macro state, and the entropy is just the logarithm of that number. So macrostates with many, many microstates are high entropy, few microstates are low entropy. The interesting thing here is a real physical system will have, in this classical way of thinking about things, has a microstate, and therefore it has an entropy. Once you define the coarse graining, once you define the macrostates, the entropy is an objective fact. In the Gibbs/Shannon way of thinking about things, we say, well, I don't know what the microstate is, but I have some guess, knowledge, information that I sum up into a probability distribution over possible microstates, and then the famous formula minus the sum of P log P, where P is the probability of being in any given particular microstate. So conceptually, this is a very different thing. This is an objective. This has something to do with how much you know about the system. And that raises all sorts of philosophical questions. So Wayne Myhrvold, who I reference at the bottom here, starts off a talk that you can find online in a very interesting way. He says, let's imagine you have a box of gas, you know its temperature and density and so forth, and someone asks you the entropy and use the ideal gas law or whatever, you calculate the entropy, it's in equilibrium, stuff that you're supposed to be trained to do. And then the person says, oh no, but I actually have here written down the exact microstate of all the molecules in the gas in the box. Did the entropy change when he told you that? And so what Wayne claims is that physicists and philosophers gives different answers to this. He says the physicists will say, yes, because they think of the entropy as the Gibbs-Shannon version of doing things. And the philosophers will say no, because they think of Boltzmann. I'm not actually sure that's true. I should have done it as a poll, right? But the reason, and this is sort of this is going to be the lesson that you can keep applying yourself for the entire rest of the talk. The question about which entropy is the right one is a dumb one, because it depends on the circumstances and what use you're going to put it to. But nevertheless, asking the question can lead you to some interesting places. And the point that Myhrvold makes is, if you want to sort of reconcile your intuition that someone has a little piece of paper in their back pocket that gives you the exact microstate, couldn't change a fact about the system like its entropy, well, you can think in sort of a resource-oriented way, right? With the knowledge of the microstate, you could do things. And you could maybe extract some energy. If you go back to the original definition of entropy in terms of entropy or energy that you could not extract, then lowering the entropy is a reflection of the fact that there's more work you can do. And if you know the exact microstate, you can do more work. But that leads to a question of how you do the work, how you extract it, and therefore how you could manipulate the system. And all of this is potentially fruitful foundational question asking. So there's no right answer here, but this kind of thinking, one hopes, leads you to think about things you thought you already knew in different ways. One big question that is not my own area, so I'm not going to go too much into it, but one big question in the foundations of stat mech is how and why and under what circumstances systems equilibrate. There's a couple papers out there you can find. I think Brown and Upink have written a paper claiming that there should be a -1st law of thermodynamics that says that systems do reach equilibrium, right? We think that entropy increases, or at least it doesn't spontaneously decrease in a macroscopic system, but there's no law that we know of. Maybe you know something I don't, but there's no general law that says how fast entropy increases, nor even to what extent it increases. There might be a maximum entropy, but do you reach that? And their claim is, we assume that you do, and that should be a law of thermodynamics. And this is one of the other fascinating aspects of this story is the fact that things do equilibrate seems to be one of those cases where physicists are very happy to get the right answer for the wrong reasons. And there is, if you're interested, and again, it's not my particular area, but there's a vigorous debate in foundations of physics and the philosophy of physics about what is the correct reason why things equilibrate in the real world. The ergodic theorem is often mentioned, but the actual timescales that it would take for the ergodic theorem to be relevant, when you do the math, seem to be much longer than the actual timescales it takes for things to equilibrate. So you can say things that are true, but they're not actually the reason why things happen in reality, and that's the kind of thing that Foundations wants to get right. Also, and this is sort of just to put this into your mind, when you have a box of gas, now let's say you don't have a box of gas. Let's say you have a system which is an ice cube in a glass of water, and you let the ice cube melt. So now it's equilibrated. It's a glass of water at some temperature, and you're going to make predictions for its future behavior. And what you will do is have some thermal, equilibrium distribution over the possible microstates of that system, and compatible with its macroscopic features like temperature and volume and so forth, and then do the Boltzmann equation or whatever toward the future. So you're assuming some distribution over possible microstates subject to those macroscopic constraints. You know that distribution isn't right. How do you know that it's not right? Because you could imagine evolving it backward, and you wouldn't get an ice cube forming out of nowhere, right? The actual amount of phase space that is legitimately allowed for that system to have is much, much smaller than what you assume it has when you evolve it forward in time. But it works. Why is that? That's the kind of thing. It does work. I'm not saying it doesn't work, but founding exactly how it works is an interesting question. You have a question. Okay. I didn't know that was allowed. Go ahead.
Sorry. I think this might be important moving forward. In this line of thinking, what is the difference between the -1st law of thermodynamics and the second?
The second law says entropy increases. The -1st law would say it reaches its maximum. plenty of functions increase without reaching their maximum. It's actually not going to be important. Don't worry. Like I said, this is not the area I care about the most, but I'm letting you in on the lay of the land in terms of the foundations of statistical mechanics literature. There's a lot of talk about this. My area much more is the second law all by itself, right, which gives rise to the arrow of time. The arrow of time question is a fascinating one. There's many manifestations of the arrow of time in our everyday lives. Like we remember the past and not the future. We're all a little bit older in uniform ways than we used to be. But it's a question that didn't exist pre the 1800s. Like no one worried about it because obviously time moved in a direction. That wasn't a thing to worry about. But we invented Newtonian mechanics and Laplace explained it to us a little bit. And suddenly we realized that directionality was nowhere to be found in the fundamental laws of physics. So where does it come from? And the answer I and others claim is that all of the directionality to time comes from the second law of thermodynamics, comes from the fact that entropy is increasing. So there's an enormous amount of work to be done explaining why aging and memory and cause and effect are all reliant on the second law of thermodynamics. There's also work to be done explaining why the second law is true. So here's the Boltzmann version of it. It kind of makes sense. If you chunk up phase space into macro states and you start in a low entropy macro state, you will generally increase in entropy just because there are more ways to be high entropy than to be low entropy. As soon as Boltzmann said this, his own former professor objected, right? Like what a betrayal that was. Joseph Loschmidt came up with what we call the reversibility objection, saying, no, there are, by the reversibility of the underlying laws, exactly the same number of trajectories for the system in which entropy is decreasing as increasing. So you haven't derived any arrow of time at all. What is the resolution to this? And so the resolution, Boltzmann in the 1870s didn't really give the right resolution. He basically filibustered his way into, because everyone knew that entropy increased. So getting the right argument for it didn't seem like a high priority thing to do. Eventually, the controversy flared up again in the 1890s, and Boltzmann, for the first time, gave what we think of as the correct answer, what I think of as the correct answer. And Richard Feynman has also talked about it and others, but it was David Albert, a philosopher, who really put it on a firm grounding only in the year 2000, that you need to assume as part of the foundations of statistical mechanics that the early universe started with low entropy, or that one end of time has a low entropy boundary condition. You have to put an explicit time asymmetric assumption into the game. That's where the time asymmetry comes from. This is called the past hypothesis, the fact that the universe started with low entropy some finite time ago. Interesting to me, fascinatingly to me, so Boltzmann does mention this in 1895. But he mentions it, it's a very charming thing. He was very annoyed at his critics, who include Zermelo, for example. And he writes a paper and he gives 3 different reasons why entropy might increase. And this is one of them, but he doesn't say which one is right. They're all mutually incompatible with each other. So it took us a while to figure it out. So what you could have done in 1895 is you could have inferred the existence of a beginning to the universe, right? The sun is shining, it's using up fuel. It couldn't be infinitely old. Nobody did, as far as I know. Nobody in the 1890s invented the idea of a Big Bang, because sort of the background Newtonian assumption is the universe is just eternal. It wasn't until general relativity came along and you realized the universe is expanding that people really in the 1920s really took that possibility seriously. Of course, it leaves us with a huge unanswered question. Why did the early universe have low entropy? And that one, no one knows the answer to. Some of us have ideas. I have ideas. My ideas are, number 1, better than anybody else's. Number 2, not that good. So we still have a long way to go to figure out the right answer to this question. And I'll tell you, cosmologists don't think about this in the right way. They have not really, Roger Penrose being a very shining counterexample, but modern cosmologists don't really think of explaining the low entropy of the early universe as their job, but it really is. And we can talk about if you are skeptical that the early universe did have a low entropy, but it did. Trust me on that. I want to tell you one more, no, not just one more. There's a couple more fun things about StatMech that you should know. I told you why there's an arrow of time from the Boltzmann approach to entropy. What about from the Gibbs approach? If you had the Gibbs or Shannon entropy, the entropy of a system depends on your knowledge of it. And guess what? In a closed system, that's a constant. It does not ever go up. What you can do is you can look at the system, you can measure it, right? Then you learn something, and inevitably the entropy goes down because you know more about it than you did. So I have just derived a new law of thermodynamics that entropy only decreases in closed systems. Now, no one believes that's true. So how do you reconcile a Gibbsian or information theoretic approach to what entropy is, which is the one we most often use, to the idea that there is a second law? So you can actually, there's different ways to reconcile. It's not a true paradox. It's just sort of something that annoys you a little bit. Here's one thing you can do, and it's in this philosophy of being bugged by something and therefore maybe deriving something useful. You can define a cross entropy. This is a well-known thing. If you think of the entropy of a probability distribution as the probability that you will be surprised to learn an element of the distribution, the cross entropy is the likelihood of being surprised if you don't even have the right distribution. If somehow there is a correct distribution and you think it's a different one, what is your likelihood of being surprised? And so we were able to derive something we call the Bayesian second law of thermodynamics, which says you can calculate the cross entropy of the actual, probability distribution you thought it started with the probability distribution that you have after Bayesian updating. You've done some measurement, you've learned more, and you can show that the difference at early times and late times between this cross entropy only ever goes up. There is something that goes up, in other words, some entropic kind of quantity that keeps going up, even though you're just learning more and more about the system. Okay, this is the final StatMech thing I wanted to say. I would not be allowed to come to the conference without showing a picture of Maxwell's demon. I'm pretty sure that happened every time. All I'm here to tell you is that even today, people do not agree on what is the resolution to Maxwell's demon. So you might know that they thought they had it figured out in the 19th century. Szilard came along with a different explanation. People said, yes, now we've got it. And then Landauer and Bennett, much more recently, in the lifetime of many people in this room, figured out what is probably the most popular set of explanations now, based on Landauer's principle. The demon has a little notebook. You'll eventually have to erase entries in any finite sized notebook. And it's that erasure that increases the entropy of the universe. But this approach has been criticized quite plausibly, I would say. I don't want to say whether it's right or wrong, but John Ehrman and John Norton, who are two philosophers of physics, make the claim that the Landauer-Bennett argument assumes the second law of thermodynamics. So it is compatible with the second law of thermodynamics being true in the case of Maxwell's demon, but it doesn't derive the fact that even in the presence of Maxwell's demon, entropy is increasing a la the second law. So there could very well still be another cycle of someone going, okay, now we really understand Maxwell's demon. And just one way in which this intersects my own interest, and I think about it, even though not in a productive way yet. Like I said, every arrow of time relies on the second law. So one arrow of time is that we have memories of the past, but not the future. Another way of saying that is we make measurements, and then in the future, we have the measurement outcome, and in the past, we didn't, okay? But no one has really, to my satisfaction anyway, completely pinned down the relationship between measurement and entropy increase. So you might think on the left, there's a little cartoon, there's a system and, an observer and a system, and a reliable measurement is one where the observer looks at the system. This is just classical, don't worry about wave functions collapsing or anything. And the observer gets an idea, aha, I've seen the system, it is in state A, not state B. There's no way that that kind of mechanism can be guaranteed by the fundamental laws of physics, because the fundamental laws of physics, to the best of our knowledge, are reversible, which means I can always start with the later time state, which says the system is in state A, but the observer believes it was in state B, and go backward in time to find some initial condition that would get me there. You can always get to any incorrect ending point just by going backwards, starting from the fundamental laws of physics. The reason why you don't has to be because entropy is increasing. But I don't think that that has been completely accurately spelled out as yet. So that's kind of an interesting thing to work on. Let me talk about quantum mechanics. Who is timekeeping me? Yeah,
15 minutes left.
50 minutes left, good. I'll just talk fast. There's not that much to say about quantum mechanics. It's pretty easy. I do want to emphasize that there's a phrase that goes around, which is interpretations of quantum mechanics. And we don't really use that phrase in the professional circles anymore because it gives you the impression that what we're doing is kind of like literary criticism, right? We're like talking about different things and trying to get the words right. In the modern era, we really do have different theories, really truly different physical theories that sadly kind of give the same predictions, but are really very similar deep down, and they all end up looking like quantum mechanics. So that's a puzzle for us. So here's my flow chart or finding chart for where we are, where you are, depending on what your predilections are concerning quantum mechanics. Quantum mechanics starts by saying there's a wave function, and if I square the amplitude, I get the probability of getting a measurement outcome, right? Let's take that for granted. So does that wave function truly represent reality? Or, like, is the physical world a wave function or map onto a wave function? Or is it simply a tool for making experimental predictions and has nothing to do with reality per se, okay? So there's a whole bunch of people who do what are called epistemic models of quantum mechanics, which say the wave function is just a tool. There are even quantum Bayesians who say two different people can have exactly the same physical system in front of them and describe it using different wave functions because they know different things. It's all epistemic. It's like a Gibbsian probability distribution. Arguably, the Copenhagen interpretation is like this. I can only say arguably because nobody knows what the Copenhagen interpretation actually says. But there are certainly things that you can quote mine from Bohr and Heisenberg that make it sound like there's no world out there, there's only what we see, right? That's kind of an epistemic approach. If you want to be a little bit more realist about quantum mechanics, then you can ask, is the wave function the whole story, or are there other physical quantities? Other physical quantities are hidden variables. So for instance, there's a set of theories called de Broglie-Bohm theories. Last year, the Nobel Prize went to people testing Bell's inequality, and the Nobel Committee issued a press release, which was embarrassingly wrong about what Bell's theorem actually said. It said that these experiments ruled out hidden variable theories, which is just wrong. They ruled out local hidden variable theories, which hadn't been popular since 1935, maybe never popular, but Bell himself was a huge fan of hidden variable theories, including Bohm's theory. And so they're very viable right now, non-local theories that use hidden variables to explain the quantum mechanical predictions. But if you don't like hidden variables and you want to say it's only the wave function, the final question is, does the wave function always obey the Schrodinger equation, or does it truly collapse all by itself? Okay, if you think it collapses, that's an objective collapse model. Roger Penrose has a famous such model, but there's also models called GRW and spontaneous delocalization models. And the great thing is that these models really do make different experimental predictions than the other versions of quantum mechanics. You can make a Bose-Einstein condensate with a large number of particles at a very low temperature. And in these models, one of the atoms will just spontaneously localize its wave function, injecting heat into the system and then breaking the condensate. And there's experimental tests going on right now. And like it or not, if you said, oh no, I think it always obeys the Schrodinger equation, then where you live is in what is called the many worlds interpretation of quantum mechanics, or the Everettian interpretation. The Everettian interpretation can be summed up by saying, deal with it. There's a quantum state, there's a Schrodinger equation, just listen to what it predicts. And what it predicts is that when you measure the spin of a particle, you become entangled with the particle. Part of the quantum state is the particle was spinning clockwise, and that's what you saw. The other part of the quantum state is the particle spinning counterclockwise, and that's what you saw. And these are now two separate worlds. I can give a whole nother talk about that, but I don't need to. I wrote a book, Something Deeply Hidden. You could buy it right now. Any of you who have laptops open, don't hesitate. But, you know, again, thinking about these things makes one think. That's why it's a good thing to do. And you know, there's the number of thoughts that we will ever have is much smaller than the number of thoughts one could possibly have. So things that pump us in interesting directions of thought are always worthwhile. I mentioned that the objective collapse models make experimental predictions because energy is not conserved. That leads to a question. Well, what about the other model? Or is energy conserved there? No, it is not. And this is not a weird thing about Eveready, quantum mechanics, or anything else. It's just a thing about quantum mechanics that people haven't really wanted to face up to. Let's define the energy. We can always argue about definitions, but here's a definition. The expectation value of the Hamiltonian in a particular pure quantum state. And why is this a good definition? Well, if it weren't for measurements, this would be some quantity with the units of energy that is exactly conserved because of Noether's theorem, right? That's kind of what you mean by energy. But measurements break it because measurements have nothing to do with Noether's theorem because they don't obey the Schrodinger equation. The wave function collapses. This quantity is manifestly, obviously, trivially not conserved when you make a quantum measurement. If you construct, this is not pi, even though it's pi day, but this is like a table with a billiard ball or a bowling ball, let's say, something heavy. If you construct a superposition of bowling ball on the table and bowling ball on the floor, you have the expectation value of the energy, which is halfway in between. And then you just look at it. You literally open your eyes. You let a photon hit your eyeball, and suddenly you've collapsed to either the bowling ball is on the table or on the floor. Those have different energies. If you ask the physicist on the street, they would probably say, well, for one thing, why are you walking on the street in which you bump into physicists all the time? I don't know, but you might say, well, I bet, sure, it looks like energy is not conserved, but it's gone into the environment or into the apparatus or stuff like that. It hasn't. You can easily show that parametrically you can make this energy difference as big as you want, completely independently of whatever energy is transferred to the environment. And you can even suggest experiments to see energy, like we suggested an experiment where you could measure energy not being conserved. It's hard to do, but it's not completely implausible. Does that bother you? Should it bother you? I think it bothers you the least if you are Everettian, because in Everett, you have different branches, and you just say, well, there's a branch in which the ball is on the table, a branch in which it's on the floor. Those branches have slightly different energies. The total energy that you had before has been distributed slightly differently. But the energy of the wave function of the universe is completely conserved because you're always obeying the Schrodinger equation. If you like energy conservation, you should believe in the many worlds interpretation of quantum mechanics. In Copenhagen, it's just hopeless. Okay, so again, there's a lot to be done in understanding quantum mechanics, as you might know, and now we're moving slightly into the sort of thermo regime. But I'm trying to focus not on the entire set of problems, but on those that are truly foundational, the problems that you, in your ordinary life, just assume the answer to and get on with it. And I'm sort of going to not let you do that. So Schrodinger's cat, I am a cat person, so I don't like to kill the cat. I put sleeping gas in the little box there. So the cat goes into a superposition of awake and asleep, okay? And Schrodinger's issue with the whole thing, he basically invented a way to amplify a microscopic superposition to that of a macroscopic quantum superposition. And he says, you can't expect me to believe, because he was anti-Copenhagen. He was on Einstein's side in doubting that quantum mechanics was finished. And he said, you can't expect me to believe that when I open the box, it suddenly changes from a superposition to just a cat is awake or a cat is asleep. His daughter, by the way, did admit that Schrodinger did not like cats, which is why it was cyanide in his thought experiment. So forgetting about one's favorite interpretation of quantum mechanics, there is still a technical question here, which is that when you observe macroscopic systems, the number of possible quantum states that you would ever end up seeing them in is infinitesimally small compared to the number of quantum states you could imagine. We don't see macroscopic objects in superpositions of different places in space. There's a cat on the floor, there's a cat walking around. We never observe that, even though in the formalism, it would be trivial to write it down. Why? We kind of know the answer to that based on work by Zurek et al. There's the photon that I've drawn, and this particular photon would be absorbed by the awake cat and not interact with the asleep cat. What that means is a macroscopic superposition almost instantly becomes entangled with the environment and decoheres, right? And the reason why it decoheres so that its density matrix is diagonal in a particular basis is because the basis in which the cat looks positionally coherent is the one where you don't become more and more entangled, right? If you're a superposition of two different positions in space, then you're going to quickly become entangled. Then you integrate out the environment and you diagonalize. But if you're just in a coherent spatial setup, you will not entangle with the environment. You'll interact with it. You'll either absorb or not, but that doesn't generate entanglement. So there's something about the fact that the laws of physics are local in space that leads to certain states being what we observe. And these are called pointer states in the literature. But if you sort of drunk the foundations of physics Kool-Aid, that's not quite sufficient for you. So you're like, why are the laws of physics local? Why are they local in space? Why do we live in space rather than momentum space anyway? I actually think I know the answer to that one. We're working on a paper to that one. It turns out that if you write down a Hamiltonian classically as a function of x and p, right? In principle, you could write down any function of x and p you want. In practice, what real world Hamiltonians tend to look like are p squared over 2m plus some function, the potential as a function of x, right? If you have many, many particles, the potential can be a function of x1, x2, x3, but the momentum part is p1 squared over m plus p2 squared over m, et cetera. There's a distinction between the momentum part and the potential part of the Hamiltonian for typical classical systems we observe. And our claim is, because even though you could, in principle, write down any classical Hamiltonian you want, you cannot get any classical Hamiltonian you want as the classical limit of a quantum Hamiltonian. Quantum Hamiltonians that have classical limits tend to have limits of certain forms in which one observable plays a very different role than its conjugate observable. We call the one that looks like p squared momentum, and we call the one that looks like v of x position, and that's why physics looks local. But it only works if physics could look local, and I can easily write down quantum Hamiltonians that don't have a classical limit. Why do our laws of physics allow for the existence of a classical limit? You can probably get through the day without answering that question, but this is the kind of thing that we care about. It is closely related to the problem of quantum mereology, the question of how you divide up Hilbert space. You know, if you've taken your quantum mechanics course, you know that tensor products, I mean, maybe they didn't use the word, but really tensor products are the way that we describe subsystems in quantum mechanics, including the most basic one of all, which is system and environment. But the reason why that makes sense to us is because in our experience, we start with subsystems. We start with, oh, here's a bottle, there's water, there's a table. We have individual Hilbert space factors describing each of them, and then we take the tensor product of all of them. The sensible procedure. But what about the inverse problem? What about going the other way? If I just have Hilbert space and a Hamiltonian, there is a giant unitary matrix that relates a very, very large number of different ways that we could decompose all of Hilbert space into subsystems, including system and environment. Who tells me that one of them is better than the others? And we think we have an answer to this one also, but again, there's still more work to be done. If I propose to you a decomposition into system and environment, the Hamiltonian instantly gets decomposed into a system part, an environment part, and an interaction. And there's actually two things you need for a macroscopic quantum system to behave classically. One is that its wave function sort of remains localized, right? This is the Ehrenfest theorem argument that you're usually given. If you have a big, massive thing, there's not a lot of uncertainty to its center of mass position. It can just sort of behave classically. But the other thing is the thing I told you about Schrödinger's cat, right? It doesn't instantly decohere. It doesn't instantly generate a huge amount of entanglement with the environment, a good classical looking system. And so those two features, system remains localized and system remains unentangled if it starts out that way, are governed by the system Hamiltonian and the interaction Hamiltonian. And you can invent, we did invent, characterizations of remaining localized and remaining unentangled, and then show if you minimize them, you get an algorithm for picking out the right way to divide Hilbert space to give you a classical behaving system. So in principle, the laws of nature don't need to include a division of Hilbert space into system and environment. Our desires, our ways of treating things at a coarse-grained level will naturally suggest a best way of factorizing Hilbert space, which is kind of an interesting thing. So then the final thing to talk about is to go back again to cosmology, both because I like cosmology, also because Nicole said she would like to hear me talk about cosmology, so I'm adding some cosmology in here. You know, I told you that the thermodynamic arrow of time relies on a past hypothesis of low entropy. There's also a quantum arrow of time, namely, if you want to put it this way, wave functions collapse into the future, not into the past. Or if you're an Everettian, wave functions branch into multiple worlds as you go into the future rather than the past. The origin for that quantum arrow of time is the same. It relies on a certain coarse graining and the assumption of a low entropy past. So in some sense, the Big Bang gives us the ultimate quantum thermodynamic resource, not just ultimate in the sense of the best, but ultimate in the original sense of from which everything else flows. If it weren't for this special state of the Big Bang, we wouldn't have any arrows of time, including the quantum one. We would be in equilibrium. There'd be no resources to draw on. I mentioned that we don't know why the early universe had low entropy, but I strongly suspect that quantum mechanics has something to do with it. In fact, quantum cosmology, maybe arguably quantum thermodynamics has something to do with it. Is our universe a fluctuation? I think it might very well be. We have one picture of this, again, you know, very hand wavy, but you can imagine a fluctuation from empty space into empty space plus a little baby universe that starts out low entropy. And in this picture, the reason why our universe started out low entropy is because the ensemble of universes can always increase in entropy by making more universes. So there is no equilibrium. There is no maximum entropy state for the entire unbounded wave function of the universe. I would like to see more work on scenarios like this. And on the other side of cosmology, there's the far future where we enter the Boltzmann brane problem. This is something that, this was one of Boltzmann's other suggestions in the 1890s. He said, well, maybe the reason why there is an arrow of time is because the universe is usually in thermal equilibrium. But if you wait long enough, it fluctuates downward and then it bounces back. And we just happen to live in one of those fluctuations because he knew that life depended on an entropy gradient. So he invented the entropic principle and the multiverse, and he suggested it that way. The problem is, as Arthur Eddington pointed out, in that scenario, big fluctuations in entropy are more rare than small fluctuations. So if you conditionalize on getting an observer, they will be minimum fluctuations away from thermal equilibrium, what we call a Boltzmann brane, a disembodied brane that sort of randomly is assembled out of the thermal fluctuations just long enough to look around and go, ha, thermal equilibrium, and then it dies. And we are not, that's not the universe that we see. This is a picture from the New York Times with a slightly awkward caption. It's not Boltzmann's brane. Boltzmann's brane is under the tombstone with the equation on it. This is a Boltzmann brane. But the thing about Boltzmann branes, there's a back and forth dialogue here. This idea that we live in an eternally fluctuating thermal universe is arguably our current best cosmological model. We know that we have a positive vacuum energy, or at least that's the best fit to the data right now. The standard cosmology called lambda cold dark matter, where lambda stands for the cosmological constant, the vacuum energy. And the far future in that theory is that there's a horizon around us, and that horizon has a temperature, just like a black hole horizon has a temperature. It's a low temperature, 10 to the minus 37 Kelvin, but you have infinitely long to wait. So naively, the far future has an infinite number of random Boltzmann brane fluctuations in it, and that's a big problem. But then, thinking with your foundational physics cap on, you dig a little bit deeper and go, wait a minute, the universe is not literally a box of gas, it's a quantum system, right? When we say the universe has a thermal state, we mean it has a thermal density matrix. But that density matrix is static, not changing with time. So here's a question, which is an honest question because people disagree about it. In a static thermal density matrix, are there true dynamical existing fluctuations? I.e., will it be true in a thermal density matrix that there's a fluctuation that brings into existence a brane and then it goes back out again? If you measure thermal density matrix many, many, many times, you will see fluctuation. That's not what I'm talking about. There's no one measuring it here. All by itself, do static thermal states have fluctuation? My collaborators and I said no. Seth Boyd and others have said yes. I don't think that there is a consensus yet, which leaves us with a whole bunch of questions for quantum thermodynamics. I'm not going to read all of these out loud, but like I said, I'm giving you folks the responsibility of thinking foundationally about your own field. There's certainly lots of questions to ask. Some of these you'll think you can invent the answer right away. Some will be difficult. The final one is interesting. What about all those existing questions about statistical mechanics and its foundations? Does quantum mechanics solve them? Does entanglement play a role in equilibration? You know, what about the fluctuations, all this stuff? So there's an enormous amount of work here to do. I think it'll be a lot of fun. And the very, very, very final thought, we can also think the other way around. I've been suggesting ways that thinking philosophically or foundationally could be relevant to thermodynamics. Here's Barry Lower, who is a well-known philosopher, a legit philosopher, not an ex-physicist, who said, it was a shock when I realized that most problems in philosophy could be solved by thinking about statistical mechanics. And the idea is, in principle, you know, what is the world? It's a bunch of things we have incomplete information about. There's a probability that this happened, and that correlates with the probability that other things happen. And these are problems that involve causality and agency and consciousness and free will and teleology. And they're all statistical mechanics problems. So, you know, you solve this whole Maxwell-Demon thing, there's still a lot of work to be done, starting from thermodynamics and quantum mechanics. Thank you.